Hello dear students, this time we are meeting again. I want to deliver lecture number 4 on this differential equation solvable for P. After lecture number 3, you know what we did. We have actually discussed some forms. There we have discussed equations which are solvable for y and how to solve the equations which are solvable for y. Now we have another this case. I will take case second. We have differential equations which are solvable for x. That is, when we are in a position to express x, that is, x can be explicitly expressed as function of y and p. Means when you are in a position to write x as some function of y and p, how we proceed. Especially in this case, y occurs in the linear form, x occurs in the linear form, so we are in a position to write x explicitly on one side, and this x becomes the function of y and p. The procedure is we differentiate this. Let us differentiate with respect to y. You get dx by dy is equal to partial of psi with respect to y, then plus partial of psi with respect to p into dou p by dou y. This will be 1 by p will be some function of, say, g of y and and this dou p by dou y. It will be like this. This is second equation. Then what we do is we solve this equation. As in previous case, we solve, suppose let us assume equation second has some solution of the form. Say it has a solution. Its solution will be some, say, f of psi we have used. Say it is f of yp and c. Its solution is this. We assume that it has the solution of this form. Because it involves y and p, so solution will also involve y and p and some constant c. Then what we do is we eliminate p between, as usual, between first equation and third. Then we eliminate p between first and third. Eliminating p between first and third, we get the required solution. We get a required solution involving x and y and some constant. But in this case also, sometimes it becomes difficult to solve the equation. It is difficult to eliminate p. If elimination of p is difficult, time consuming, I mean, it is difficult, it takes some time, then we express x is equal to, say, some function of pc and y also, say, some function of involving p and c. This will be the function f1 x involving p and c, and y also is some function involving p and c, and these together will be the solution of given equation. In case it is not possible to eliminate p between the given equation and the solution that we have got. But if it is possible, if you can easily eliminate p between the given equation and the solution set, then that will be the required the solution. It is just like what we did in lecture number 3rd. There we have done some these rules. When y, then when equation can be expressed as a function of y, that is y is equal to some function of p and x, what we did there, and here x is equal to some function of p and y. There was y as function of p and this x. Here is x function of y and p. Let us have some applications. Let we take some applications on this, so that you will have. I will take a question here from the book. Let me take a question. Solve the differential equation. Suppose we have to solve the differential equation. It is y is equal to 3px plus 6p square y square. This is the equation that we want to solve. Solve this equation. This is not the equation which is solvable for y, because it involves y square on this side. But here we observe that x is existing in linear form. We can solve it for x. I can write it as 3px is equal to y minus 6p square y square. This means x is y by 3p minus 6 p square y square by 3p. So you have x is equal to 1 by 3 y by p minus 2 p y square. It is 2 p y square. So it is now what? It is solvable for x. We could solve the given differential equation for x. By x I mean we could write x explicitly on one side, x, and y and p on our other side. How we go then? Let us differentiate this now. Differentiate with respect to y. When we differentiate with respect to y, how we proceed? It is dx by dy is equal to 1 by 3. Okay, here I will have to use division rule. It is denominator square, it will be p square, p as it is, derivative of y is 1, minus y as it is, derivative of y is dp by dy, because we are differentiating y with respect to with respect to y. P is a function of y also. Okay, minus 2. Here you can go by the product rule. It is y square, derivative of y square will be 2y with respect to y, p as it is, then plus y square as it is, derivative of p is dp by dy. Let us verify this, simplify this. I will write two equations on this side. I may need them later on. Number this equation, given equation, y is equal to 3px plus 6p square y square, given equation, and x is equal to, let it be there, we have, I will rub it, I don't need it now. How we proceed, you see, this is your 1 by p, because you write dy by dx as p, dx by dy will be 1 by p. Okay, this is your p minus y dp by dy by 3p square, then minus this is minus 4 yp, then plus minus 2y square dp by dy. Now we have to simplify this. We have to find out the solution. How we proceed? Okay, this you can write. This is 3p square, or you can take here LCM. Let us take LCM. 1 by p is equal to 3p square. This will be p minus y dp by dy minus this is 12p cube y, then it is minus 6p square y square dp by dy. This will be 3p is equal to p. Let me connect the derivative this. I will connect this with this. Let me see what it gives me. This is your p minus 12 p cube y, take minus y dp by dy. This is 1 plus 6 p square y, 1 plus 6 p square y. Now what about here? It is 0 is equal to, this is minus 2p minus 12 p cube y minus y dp by dy into 1 plus 6 p square y. You can write this 0 is equal to, you can take minus 2p common. This will be 1 plus 6 p square y is this. This is 1 plus 6 p square y minus y dp by dy into 1 plus 6 p square y. Okay, you have got the same factor here, factorization. It is 0 is equal to 1 plus 6 p square y into minus 2p minus y dp by dy. Okay, so that means you have got this. In this way you can write, this implies it is taking minus outside, 2p plus y dp by dy into 1 plus 6 p square y is equal to 0. We again reject this. We do not take this 0 because it does not involve a derivative. Even if we take this 0, we get the value of p, then solution will be singular solution. Therefore we take this 0, we take the help of this as usual. This means 2p plus y dp by dy is 0. This is 0. Now here you can easily separate the variables. It is variable separable. It is the variable separable form. We can separate the variables. This you can write 2p is equal to minus y dp by dy. This gives you 1 by y dy is equal to minus 1 by 2p dp, or you can write this twice 1 by y dy plus 1 by p dp is 0. So variables got separated. Integrate. When you integrate it, it is twice log y plus log p is equal to log c. Okay, you use it. Now you find out p. If you can easily eliminate the p, this will be log of y square plus log of p is equal to log c. That means log of p y square is equal to log c. So that means you can easily get here p. P is c by y square. You have got p is equal to c by y square. So you can eliminate the p between the given equation and this solution. Use value of p, use value of p in first. What was our first equation? Given equation, use it in a given equation. That gives you y is equal to 3x, the value of p is c by y square plus 6y square, p square is c square by y4. And what is its solution? Its solution is y is equal to 3cx by y square, this is plus 6c square by y square. That means y cube is equal to 3cx plus 6c square. This is the solution of the given differential equation involving only x and y and not p, because we could easily eliminate p from the solution and the given equation. This is the solution, complete solution of this differential equation. In case it was difficult to eliminate p, then we could write x in terms of p and c, y in terms of p and c, where c is constant. Okay, let me have let us take one more example we can take. Let us write, we have to solve, say it is solve suppose you have to solve this differential equation. Here you have y occurring in square power log, y is in log. So we are observing here we can write this equation as a function of y and p. It is solvable for x because x exists here linearly. I can write x py is equal to y square log y minus p square. This is x is equal to y square log y by py, then minus p square by py, so that you can write your x is now, this is your first equation, your x will be now, it is y log y by p minus p by y. Now how you differentiate this? This is x on one side, on other side you have explicitly y and p. So it x is solvable, this is solvable for x. Let us differentiate this. Differentiate with respect to y. When you differentiate, what you get? Dx by dy is equal to, here division rule, p square, because p is a function of both x and y. Then derivative of this y log y, derivative of y log y. Derivative of y is with respect to y 1, log y as it is, then plus y, derivative of log y is 1 by y, p here as it is, then plus y log y as it is, first derivative of p is, then dp by dy. I will again repeat this. I have to differentiate this, take this u by v form, denominator square, denominator as it is, derivative of numerator with respect to y is this, then minus numerator y log y, then derivative of p is dp by dy. Then minus here you will write derivative of p by y, it is y square, y square here, it is y square, derivative of this is y as it is, dp by dy, minus p as it is into derivative of y with respect to y is 1. So you have to now simplify this. Simplify. This is 1 by p is equal to log of y plus 1 into p minus y log y dp by dy by p square minus y dp by dy minus p by y square. You can take p square y square LCM. It is 1 by p. Take LCM here, p square y square. This is y square into log y plus 1 into p, or you can split it first. You can write it in this way also. This way you can write 1 by p is equal to 1 plus log y p by p square minus y log y dp by dy by p square. You can go this way also, minus y dp by dy by y square plus p by y square. You take this here, connect these two terms. You connect these two terms, you see what you get. You can write 0 is equal to it is 0 is equal to, take common, it is minus y. You can take, one is y dp by dy, take y and dp by dy. This is log y by p square, log y by p square plus y dp by, it is plus 1 by y square. It is this factor. Then you have plus 1 plus log y into p by p square minus 1 by p plus p by y square. You see what you can get from this. It is 0 is equal to minus y dp by dy. It is log of y by p square plus 1 by y square. You can take common here. Take from this factor you can take common. I will first simplify this. It is p by p square plus p log y by p square minus 1 by p plus p by y square. This term will not survive here, it gets cancelled. So it is 0 is equal to minus y dp by dy into log y by p square plus 1 by y square, then plus you have these two terms here. Now you can take p common. Now it is log y by p square plus 1 by y square. So this factor and this factor is now same. You have the factors same. You can go this way. You have the same factor. You can take it log of y by p square plus 1 by y square. Inside you will get minus y dp by dy plus p is equal to 0. Is it okay? Minus y dp by dy, this factor and this factor is same, and you don't take this 0, you take this 0. It is minus y dp by dy plus p is equal to 0, and here variables are obviously separable. You can write here y dp by dy is equal to p. This gives you dp by p is equal to 1 by y dy. It is log p minus log y is equal to c. I have integrated this. Integral of 1 by p dp is log p. Integral of this is 1 log y. I have transposed this side so that I can write it log of P by Y is equal to log C. That means your P is YC. Yes, here also you can eliminate. Use P is equal to YC in given equation. This is the form how we have case second. Case first we discussed when we can express y as a function of x and p, that is equation is solvable for y. Then second case we took when we can write x as a function of y and p, that is it is solvable for x. These are two cases. Now you will have two more cases, but they are also connected with this. You have two more cases. You have case number third. Case third means when x is missing in differential equation. You get the differential equation where x is missing. We say that this differential equation is such that x absent. In short, we say in this differential equation x is absent. When x is absent, this means the differential equation involves p and y only. A relation between what? P and y. When x is missing, actually in such equations we have seen that x, y and p is involved. But if x is missing, that means differential equation will involve only y and p. Now if you can express, if in this case if p is some function of y, x is absent now, there is a relation between what? P and y. If you can write p as a function of y, that means this p is your dy by dx is equal to some function of y. You can solve by variable separable method. You solve this by variable separable method, that will be the solution. Now in case number third, if you have like this, if y is equal to some function of p, how we proceed? If y is some function of p, then we proceed, do it by case first. That is your lecture number 3. For that you switch to lecture number 3. What we did there when we could write the differential equation y solvable for y, then you have to, what you have to do here, you have to differentiate with respect to x and go so on. You can, this is how we have case first when differential equation is solvable for y, case second when it is solvable for x, case third when you find a differential equation where x is missing, we have there only y and p. Either y will be function will be y is a function of p or p is a function of y. So in these are two sub cases of the case third. Then we have case fourth, where we have case fourth is when we have y missing, y is absent, that is differential equation will involve only x and p. How we proceed? With this I conclude here. I will be meeting you in next lecture, dear students. I hope you are revising these lectures. Thank you very much. Thank you.